Well, good morning. This is Bill Ragsdale here at the Silicon Valley 4th Interest Group meeting of June 26, 2021. And I'll be talking today about an expansion of a talk I gave some time ago on fourth matrix programming. This one is Don't Fear Deep Stack, which will explore the implications of having a very large number of parameters on the data stack. As an introduction, we need to be reminded that matrices have 4 levels of access. First, we need the matrix memory address for the data itself, the cell size, in this case 8 bytes, which accommodate floating point numbers, the matrix size in rows and columns, and then finally, within an application, the offsets within the matrix. A reminder here that fourth matrix addressing is 0-based, whereas traditional matrices are 1-based. Some of the realities on matrices. We'll see that the matrix support requires a large number of parameters on the stack. These parameters are usually hidden at the top levels, but as you get lower and lower toward the actual manipulations themselves, the number of parameters do expand. For example, one matrix requires 8 parameters to locate an individual storage cell. We know the memory address, the cell size, the number of rows, columns, the number of rows to and from, and the number of columns to and from where the data is extracted. For arithmetic, actually up to 24 parameters involved when we're manipulating 3 matrices. The good news is that this can be brought down to 5 parameters per matrix, but at the detail level of 3 matrices, it turns out to be 15 parameters to do arithmetic. Well, how to cope with this? You could use 15 variables and offload all your parameters, or 15 locals, or you could do deep stack manipulation within a small number of low-level words. So why offload the 15 values into variables and then turn right around and have to reload them to do the actual program execution? We'll examine these different levels of application words. Our starting point is to create a matrix. The top left, we see 3, 3, create A brace. We have now created the matrix A. We'll fill it with a series of numbers. In this case, each cell contains its row and column number. The top left is 0, 0. The bottom right is 22, which means the second row, second column. Throughout this talk, we'll be using 3 matrices. The first 2 are loaded, as we showed above, with their row and column number, and the C matrix, it will begin empty. We'll see examples now of 8 different manipulations of addition. The first is simply adding 2 matrices together and placing in a third. We take A plus B, add them together, and store in C. At the right-hand side, we see at the top the A matrix, in the middle the B matrix, and at the bottom the C matrix, which has the sum. And we'll see then that the C values are essentially double because we've added the A and B together, which are identical. The code is fairly straightforward. The definition for the plus sign is in the middle left. We execute 3 brace expand and then use a word subplus. The subplus is a very, very busy word, and we will see that in use in each of our applications. Instead of adding complete matrix, let's just add select rows. In this case, we're going to take a common row, row number 1, which is the middle row. So the code to execute this would be ABC 1 and then R plus, R being row selection. On the right-hand side, we see in green the middle row of 10, 11, and 12, the corresponding row in the B matrix, 10, 11, 12, and the bottom right in green, the total, which is 20, 22, and 24. The code to execute this is on the left-hand side, the definition of R plus. In this case, we're manipulating the stack and expanding the parameters necessary for subplus. But remember, you do not see that complexity at the application level. Now we can sum independent rows. For each matrix, the row will be individually specified. At the top left, we say A0, so we're going to take the 0 row of A, B1, we're going to take the 1 row of B, and C2, the 2 second row of C for the destination. The operator is RRR plus, which reminds us that we need 3 row specifications. On the right-hand side in green at the top, we've taken the 0 row. In the middle matrix, we've taken the second row. And then on the C matrix at the bottom, we've taken the final row. And again, in the middle left, the definition of RRR plus. But remember, you don't actually see this in an application. This is just in the internal programming. We'll apply the same logic to summing common column. In this case, it's going to be ABC1 and then C plus. On the right-hand side, we see we've taken the center column 1, 11, and 21 from A and B, added it to the bottom matrix, 22, 22, and 42. Now we're going to add independent columns, a little more involved. In this case, we go at the top left, we go the A matrix specifying column 0, the B matrix specifying column 1, and the C matrix specifying column 2. And they appear to be added sort of on the diagonal. We will see the 10, 0, 10, 20 on the top, 1, 11, and 21 in the middle, and the total being put in the second column, 1, 21, and 41. In this case, we have 6 input parameters, which are expanded to 15, which goes into that operator Subplus. Taking it down to a very, very simple level, we can now do arithmetic on a single cell. In this case, we're specifying for matrix A, B, and C, the 1, 1 matrix, which is the center, and then RC plus, which is row column addition. We see on the right, we've taken the top 11, the middle 11, add the 2 together and store them in the 1, 1 position for the number 22. Now we're getting a little more involved. We are now doing submatrices. This would be identifying a section of the individual matrices, but uniform across all 3. So for our A, B, and C matrix, we are specifying a common cell with row 1 to row 2, column 1 to column 2, expressed as 1, 2, 1, 2, and then complex, meaning a common submatrix. And on the right, in green, we can see the highlighted areas that were taken. The submatrix contains 11, 12, 21, and 22, added to the same value, and at the bottom right, we get the total of those 2 submatrices. And again, on the center left, the definition for complex. Again, all of those rolls and overs and R's are to align properly all the parameters necessary for the Subplus operator. Now, this is the most general case. In this case, we are adding 3 independent submatrices. From the A matrix, we're taking the 0, 1, 0, 1 submatrix. For B, we're doing the 0, 1, 1, 2. For C, we're taking the submatrix 1, 2, 1, 2. So we go from the top left corner of A, the top right corner of B, into the lower right corner of C. In this case, we have to input all 15 parameters for the addition, and they go directly into Subplus. Here's a summary now of all of the potential operators. We see we have 8 categories. We have matrix addition, the common row addition, the independent row addition, common columns, independent columns, single cell, common subcell, and finally the independent subcell. Just about all the imaginable combinations of matrix manipulation. But we need them across not only addition, subtraction, multiplication, and division. So we end up with a family of 32 arithmetic operators. But look at the arrows, the red arrows at the bottom. They all lead to the word paren, bracket, SubX, paren, or SubX for short. That is, all 32 of those words are expanded and drive into a single word, which you might examine, might consider to be our fourth arithmetic engine. Here's the pseudocode for SubX. About what you expect. First, we check the input ranges. We then copy C to transient. Over all the rows and over all the columns, we retrieve a cell from A, retrieve a cell from B, do the math operation, add, subtract, multiply, divide, and store the result into the corresponding cell in transient. We loop over all the columns, over all the rows, and then finally copy the transient variable back to C and clean up the data stack. In this case, we use the transient matrix as the destination because it is possible to do this manipulation all on one matrix. You could be taking a submatrix from one area of A to another area of A and placing it back into A, and we do not want to have to worry about the order of execution. So we do all of this through an intermediate matrix transient. Here's the D chart of SubX, just as we had in words before where we check the range. We then copy C to transient, we set up the loops. In the middle, we go over all the rows, and then on the right-hand side, we go over all the columns. We're fetching a floating point number from the A matrix, fetching a floating point number from the B matrix. We do the math operation. We store back into one cell of transient and then go to the next column. When the column's completed, we go to the next row. When the rows are completed, we come back to the bottom left and we copy transient back to C, and we drop, in this case, what are 11 parameters that are on the stack at this time. Here we reach the magic math operator, SubX. This is where all the work is done. And you'll note, as we mentioned, there are 15 arithmetic operators on the stack, parameters on the stack, and then F plus, or the operation, the math operation we wish to do. So at the top left for A, we have the specified row and columns for the A matrix. For the B matrix, the same way, the rows and columns specified, and for C. The code itself, this mirrors the pseudocode we saw before. The first two rows ending in 3 range valid question mark do range checking. Then the next 2 lines are setting up the rather elaborate looping structures. And then down in the middle, we have nested do loops. In blue, we see the arithmetic to fetch the first value. The second blue row is fetching the second value. We then execute the particular math operation, add, subtract, multiply, divide, and then place it back into transient. Loop loop takes us through the full stacks, the looping structures. And then finally at the bottom line, transient is copied back to the C matrix. And we then drop the parameters. There's 4 drop, 4 drop, 3 drop, get rid of the 11 parameters that are in use. This appears rather complicated. It certainly is. It took me about 6 hours over 2 or 3 days to develop this. I did it in pieces. I wrote it and rewrote it and rewrote it, I believe, 4 times. Wrote out elaborate stack diagrams. But once it was written, it is done, done, done. And now it's available for use by all of the other 32 operators. Even though the matrix manipulations may look complicated, and there certainly is a huge amount of stack manipulation, at the bottom we see that the execution for adding A to B, storing in C, 1,000 times is 16 milliseconds. So you can execute a 1,000 matrix set of calculations, and it still only takes 16 milliseconds. The execution time for one addition or one manipulation is 16 microseconds. So let's examine what we've seen overall. First, the routine manipulations we see in the math are pretty straightforward. As we saw, the expression is clear. We specify matrices and then some selections, and then finally an operator, add, subtract, multiply, divide. A few of the words need up to 15 parameters. However, this is shielded from our view, and generally we're only worrying about a very limited number of parameters, 2 or 3 or 4. And as I mentioned earlier, the alternative would be to unload those parameters into variables or values and then reload them when needed. So they're already on the stack. Let's just get used to the fact we can use pick and roll to manipulate very deeply into the stack. And the major effort in creating those few complex words saves the specific coding and the space for many, many, many words. Here's a comparison. In the matrix languages, MATLAB and Octave, they have very elaborate syntax available. I've made a hypothetical demonstration here that probably is not realistic, but it shows you the interlocking parameters, brackets, parentheses, and that nest. The order of execution is not at all clear, and the syntax is not at all clear. In matrix fourth, we replace this complex syntax with many single function words. Each word has a crystal clear syntax, and of course, you may create your own special purpose words. And because all of the work is done by individual single words, the testing becomes extremely easy. Well, we've seen how simple stack manipulations for matrices have at their root some very complicated structures, but those complicated structures are shielded from our view usually. I'd like to thank the late Dr. Julian Noble for the key concepts of the matrix structure, the syntax, and the parameter use. This was drawn from his book, Scientific Fourth. It is obscurely located on GitHub if you can find it as a PDF. I'd like to thank again Andrew McEwen and Tom Zimmer, who created Win32Forth, and then the European team who updated it in the early 2000s. For reference, this material is on GitHub, and through the Forth interest group, it's posted online. And also on GitHub, you'll find my 80-page book on Win32Forth, the Win32Forth guide. I'd like to thank you all for your rapt attention today, and now we will go back to mission control.